Okay, so it seems I need a little clarification here. I was going through the homework problems and I think I did the wrong ones. So in number 4, it says to check that the projection or the variance of the data projected to phi1 is the same as phi1 transpose C phi1. And I had mixed that up with this bottom one where we're taking the variance of the projected data to be the first basis vector. So I was talking about number 5 when I was taking the eigenvectors. For number 4, you do not need the eigenvectors of the covariance matrix. The phi1 is the phi1 from the original problem, right? This is your phi1 in number 4. And so when you're talking about phi1 transpose C phi1, that's this phi1. And then it's the normal, it is the covariance matrix that we computed before. Okay, so sorry about getting that a little bit mixed up. But I see that number 6 should have a little bit of clarification as well. So what happens if we retain 2 of the basis vectors? How much variance is explained by them? So where does that come from? That comes from this discussion in the previous page here, right here where we're talking about speaking of rank. And so the lambda hats are the eigenvalues of the covariance matrix, which we have already computed. And so you could ignore this left-hand side, but we will want to normalize our eigenvalues so that our eigenvalues are all positive and sum to 1. Okay, and then we keep enough dimensions so that the sum, this is the partial sum of the eigenvalues, is greater than or equal to some boundary value. So usually tau is like 90% or something, 0.9. And then so r is the we have to use at least r eigenvalues to get to like 0.9, and any less, the sum of any number less would give us less than tau. Okay, so let's see what happens in this example. Okay, so I believe our eigenvalues were in D before, right? And there they are. And so what happens when we square those? So do you remember how to do that? NP square D. Oh, I don't need to square. I'm thinking of the singular values. What am I doing? I'm normalizing these. So we take D divided by the sum of D. And what do we get? And so you notice that these are positive, less than 1, sum to 1, right? And so what happens when we sum the first two? 0.967, 0.967, right? So that's about 96.7% of the variance is explained by the first two eigenvalues, or the first two dimensions. Okay, so that's kind of the argument for, which problem was that? Oops. Hopefully you won't get nauseous with these pages flying up and down. So that was number 6. Okay, so now in number 7 we want to load the clown data, and so I just wanted to mention about how to load an image into into Python and then work with it there. So let's take a look at that real quick. Okay, so how do I load a matrix in? I'm not sure. Let me pause here for a second and load up the right script. Okay, so we're not actually loading an image. I should say we're loading a MATLAB data file, right? And so we've got the clown data.mat matrix. Let's see if I can spit this out. Clown data.mat is a MATLAB binary file that is available on our class website. And so that's where this import scipy.io, that has a nice function called loadmat, which will load MATLAB binary files. And so you load that binary file into mat contents over here, and then we extract the matrix X from that. Okay, and so yeah, so then let's go ahead and run this piece and see what happens. I should break my uh, scripts into cells, huh? That might look better. Okay, so what do we have here? Where's my, let me see if I can find my variable editor. Okay, so I undocked my variable explorer, but you can see here x is now 200 by 320 matrix, right? And so it's an unsigned integer, but that doesn't seem to be a problem with any of the operations. Um, and so now we can just treat this like any matrix. And I should say, yeah, all the all the NumPy operations work on that. Okay, so you can take the np.mean of x, and then you can take the SVD of x. Okay, well, mean subtracted first. Um, yeah, and so just a note on the, um, let's see, maybe we can take a quick look at the SVD. So I'm going to assume that you have mean subtracted, double centered, in fact. I ask you to double center it. You have double centered the centered x. Okay, but I'm going to assume that we're going to be doing the SVD on x, so that would be US, whoops, I'm using MATLAB notation there. Wait, that was just right off the bat. This is V transpose now, so remember that. Equals np.linalg .svd, and then our x, or your whatever your matrix is called that has been mean subtracted. And then for the economy size, say full matrices equals 0. I think there's an underscore there because I got caught on that before. Uh-oh, didn't I get my linear algebra? I thought I did. Oh, okay, I should have spelled that correctly. Computers only know what you type and not what you mean to type. Okay, there we go. Oh, you can't see that anymore. Sorry about that. Let me bring that up. Okay, there you go. There's our SVD. And again, if we bring in our variable explorer, we can take a look at those variables. It's always good to check your sizes. I'm always constantly checking the sizes to make sure the dimensions are matching what I think they should. And so in this case, our matrix U is 200 by 200, so that will be correct. The matrix V is 3 by 3, and the matrix S, actually it's going to be a one-dimensional array, right? It should be, S should be 200 by 3 and a diagonal matrix, but that's fine. Okay, so then, yeah, how do you compute the coordinates? I'm going to leave that to you. However, let me clear out some space here. So I'm going to assume that you have constructed the coords matrix, which is going to be 2 by the number of data points, which is how many in this case? 320. Right, so I think you remember how to do that. So that's the low dimensional representation of our 320 column vectors in our 200. Okay, so then the question is how do I plot this, right? So that's what I wanted to talk about real quick. So I just wanted to give you the command for how to plot. So you can use the plot command, but you can also use the scatter plot command. So PLT is coming out of pyplot, right? So plt.scatter, and then coords, remember to put 0 there instead of a 1, and a 1, so coords. Yeah, so this will be a scatter plot of your data points. Good. I would enter this right now, but I didn't actually compute coords yet. Okay, finally, the reconstruction back into R200, because this is R2, right? We need to go back into R200. That's going to be recon. And so suppose that recon is is 200. Whoops. 200 by 320, right? And it's been reconstructed. And so how do I show recon? It's plt.mshow recon. Oops. Okay, and so that's how you do that. And then while I'm here, let's just go ahead and take a look at the clown, just so you can see that the mshow actually works. And there it is. All right. You could load in the other color map, but this is fine, just to leave it with the default color map. Very good. Okay, so we made it through the homework. That ended up being a little bit longer than I thought, but hopefully you've got a really good sense um, for the computations we were making. That's what I'm trying to say. Okay, see you later.